We get started? Okay. So just want to quickly remind you of what we did yesterday. We talked about wrinkling in one dimension. And there, if you recall, the new element is your substrate energy. There's the bending energy we've been dealing with all along. And then again, there's tension times the inextensibility, some Lagrange multiplier times the inextensibility. Okay? This is the thing with inextensible things, they can actually sustain force, right? But even if they don't change length. So this thing is just your B times 4 derivatives of, let me write it as energy curvature squared. This is, okay. And then we found that, you minimize this, you get a wave number that has to do with the substrate, has to do with bending energy raised to 1/4 power. Could have done this by dimensional analysis, you would have got the right answer. Yeah? And then I was following this paper that pointed out that once you have the answer for one kind of substrate, it's easy to export the answer to other kinds of substrates. So we talked about that a little bit. And this is a little bit less clear than this stuff. Then we talked about folds, right? So you have delocalized solutions over there for one-dimensional compression. And then we said that there's an onset, observed onset at which both in simulation and experiment where all the wrinkles go away and you get a fold. So we talked about the onset, we talked about the size scale of these folds at onset, we talked about the energy of these folds at onset. I won't write down this stuff. I won't write what we found. Then we talked a little bit about deep folds. So deep folds is an exact solution. The exact solution goes all the way from onset to self-contact. Okay. And then there's really deep folds, where you go well beyond self-contact. And there I gave you these scaling arguments from a different paper. So if you remember, what you achieve over here is, you find two kinds of folds, right? We found this, and then we saw these fellows. Both are ways of hiding material. We saw symmetric and antisymmetric folds. To this point, these are degenerate. When you make very deep folds, the antisymmetric fold wins. I left this whole thing with some puzzles. The puzzles were these localized solutions seem to be great things to hide material with. Why bother with wrinkles? And yet, almost everything has wrinkles, and then there's a finite onset, and then you see these kinds of solutions. So there's some system size issue that has yet to be fully sorted out here. It may be a system size issue or maybe something to do with barriers. The other little bit puzzle that was there is, in the pictures I showed you, you would see more than one fold. It seems like there's some characteristic size for folds, some characteristic separation between folds. Certainly in nature that is probably useful. But there's no reason to have more than one fold. One fold can do the work of many. Just keep putting more and more and more material, right? You just pay for these bubbles. These two bubbles you pay. You can separate these bubbles as much as you like. Or you can push the bubble as deep in as you want, rather than make 3 different places where you store this. So that's what we finished. And then we started talking a little bit about two-dimensional situations. So, yeah, please ask your question. Good. So he's asking, can you go and look at the fold and say what must have been the force that created the fold? So if you recall, the barrier to make a fold, the force keeps increasing, and then you hit a barrier. Beyond that point, it flattens out the energy. So there's not a lot more information than you can get about onset. Let me think a little bit more about that one. Pressure differences. Here you don't have a big pressure difference. Yeah, you start with a planar. You start with a pretty planar surface. The next thing we started talking about is I started showing you pictures of two-dimensional situations where you get wrinkles. And I said there's a problem there. Okay, so the two-dimensional situations I showed you were, I started off with, all of these were, I picked the example of a fluid foundation. And I showed you one where you had something that looked like this. You put a drop of water on it, and it makes a wrinkle pattern that looks like this. Okay? Then I showed you one where you have a spherical substrate, and you start putting something on it, and it makes wrinkles on the outside. Then we talked about one where you push something into the substrate, right, with a finger or something, and then you start seeing wrinkles on the inside here. What unifies these three things are that they all start off in good axially symmetric states. These are the simplest 2D things you can think of to do. Okay, and I said there was a problem with all of these. The qualitative mechanism for producing these wrinkles is fairly clear. In all of them, you're taking perimeters of circles, you're putting them into places that are too small for them. They decide to solve the problem by going out of plane rather than contracting. So qualitatively understood. Now, quantitatively, how do you go about understanding it? You follow the same program we did earlier. You try and solve for stresses in the unwrinkled state. You ask when the unwrinkled state becomes unstable, and that new unstable state that builds on the last stable state, what's the favored number of wrinkles over there? Very much like the program we followed in our one-dimensional situation. And the point was that you got many wrong answers. And today we're about to tackle that and try and understand why. I'm not going to actually use one of these examples to work with. These were experiments that were done and were unexplained at some level. And then there was a very nice theoretical construction that suggested, why not look at things that are purely planar to start off with? So now I'm looking down on the experiment. The experiment that was, the thought experiment was this. Let's take a flat annulus and pull here and here. Pull inwards and outwards with different forces. Okay? So, okay, if you don't have this hole and you pull outwards, you just stretch this whole thing. Isotropic tension. If you make this hole and you put the same force here that you get here, it's as if the hole wasn't there. But if you pull inside with bigger forces than you have on the outside, then you get the same effect. Everything gets pulled in. It's like pulling in material of a skirt, at the waist, and things get folded. Get the geometry? So, sorry, this was a theorist's construction, but after that, we and others also went and constructed the experiment. So this is what they have in mind. It's named the Lamé problem after that same old Lamé whose coefficients we've been writing down. The lambda and mu belong to him. This is solved. The unwrinkled problem was solved ages ago because this is an important engineering problem to solve. This is a pipe with different pressure inside and outside. And you want to know when the pipe will collapse, and you want to know when the pipe will burst outwards. So you want to solve this problem. So this is solved ages ago in classical elasticity, but this is just a 2D version of the same thing. can just tell you briefly how the experimental realization is done. I'd hoped to bring in a demonstration today, but probably tomorrow. We did this in the lab and some unexpected things happened. So the idea is here, you have this floating thing. So it's inside, it's floating on the surface of water. And what you do is you lower the surface tension inside here relative to outside. Okay, that's what you do. So this is water, high surface tension, stretching this flat. Now you lower the surface tension there just by putting some surfactant material, so everything gets pulled in. Okay? No, I'm so sorry. Absolutely the opposite. You have water with high surface tension here. You put a little bit of surfactant on the outside so that the inside pulls harder than the outside. What is the dimensions of these things? Okay, I haven't said much about experiments so far. These many plasticky, golden brown looking things, the thin dimension is 10 nanometers to a few hundred nanometers. The lateral dimensions are millimeter to centimeter dimensions. So this, if you ask von Karman number that we're talking about all the time, let's do 2 centimeters divided by 20 nanometer squared, which is minus 2. How much does that? Help me out, please. 10 to the 12? 10 to the 12? So these are von Karman 10 to the 12. In that range. These are just normal microscopy. What you're seeing is you see nothing if the thing is absolutely flat, but you're coming in at a small angle, so you see reflection whenever there's a rippled surface. So this is how the experiment goes, and now let me tell you how we should think about this experiment in this framework. So I wrote this giant thing over here, but don't worry, we won't deal with the giant thing all the time, which I suppose means we'll deal with the giant thing some of the time. But you remember how we started off with, we had, sorry, I've gone into the forbidden zone, but it's okay. I'm not going to show much with this. This is, remember the first equation, von Karman equations we had is dj sigma ij balances the in-plane forces. Now there are 2 of them, okay? And these are the 2, okay? And then we had one that said that you take the bending and you balance, with the curvature, you balance the forces that are trying to curve you. So there's normal forces, and this thing looked, I actually didn't write it out, but we wrote it out yesterday. You know what I'm talking about, right? That B, 4 derivatives of psi minus sigma times 2 derivatives of psi in cylindrical coordinates. In 2D, it looks uglier, okay? So you don't particularly need to write that thing down, okay? In fact, you don't particularly need to write anything down because I'm posting, but I won't use all that stuff, okay? And then, there's Hooke's law, which relates strain to, and then there's strain related to displacement. This is the whole set of things you have to deal with. And they just look uglier than they're used to in one dimension. But that's why I kept in one dimension, though there's only one tension, I kept writing sigma y, sigma y everywhere, just to remind you that actually there are other things we're not writing. Okay, so I'm going to now try and work with this Lamé problem, and which will be a much simpler version of this stuff, okay? So I have this thing, all right? And I'm pulling in with some tension inside, and I'm pulling out with some tension outside. And you can already guess that interesting things only happen when the tension inside is bigger than the tension outside, right? tension outside is very big, then everything just expands nicely. Everyone's happy. So these things already tell you the boundary conditions on some of those things. So sigma r on the inside is T inside, sigma r on the outside is T outside. Okay? And now the idea, remember what we did with just 1D Euler buckling is solve the planar problem first. Okay? So put this thing equal to 0. Okay. Bear with me, we won't go to the terrible end. We'll just set it up and then I'll start telling you answers, okay? But I just want you to know the shape of how things go. So in Foppel-von if there's no things out of plane, life looks much easier, or at least it looks easier. So force balance just looks like this. That third equation doesn't exist because everything is flat. And the first equation is this guy plus 1 over r sigma r minus sigma theta. Theta equals 0. This is force balance along the radius. And del theta sigma theta equals 0. Okay, this is along azimuthal direction. So solve, he said happily, and assigned it as homework. Actually, they look a little bit simpler than they deserve to look. Just remember how you solve this. Now you need to put in stress-strain relationship, write it in terms of strain, then you need to write the strain in terms of displacements, then you'll get something you can solve. Okay? I'm happily saying solve, and we can try working on it if you're stuck in the hour for that kind of thing. Okay? So, but the solution is this. That's the radial tension as a function of position. Did I do that right? Well, maybe I did that right. I'm just going to write this ratio. So I've written tau. Tau is just, for me, T inside divided by T outside. This plays the role in this problem of the delta divided by W that we had earlier. This is the thing that forces compression. Okay? You tune this thing, you start getting compression somewhere, and that's already what the solution tells you. Huh. Oh, sorry. I've actually given, these are simpler solutions. These are solutions for R outer going to infinity. This look even uglier for, thank you Abhishek, I should have said that. And actually you saw in most of these wrinkle patterns, they don't reach the edge, so this actually gives a fairly good representation. This thing will look a lot uglier, but recover the. So you can begin to see already in the algebra what you saw by common sense here. This thing is trouble, right? This thing can turn negative, all right? So for large tau, you can get negative sigma theta theta. Okay? At r bigger than some values. So let's see what those values are. This is 1 plus 1 minus tau ri squared over L squared. I want to see when this thing shows up. And this gives you L squared. Goes as ri squared tau minus tau critical, where tau critical is 2. Okay? So this is a formula for the length of the wrinkles. You see what's happening? In here, inside this length, sigma theta theta is less than 0. This circle is defined as the place where sigma theta theta hits 0. All right? So this is what common sense told us we should find somewhere. We should find compression if you pull hard enough on the inside, and that's what you find. So this is a prediction for where you should start getting compression. And so in the Euler buckling problem, this is when you first start with non-zero delta over W. Okay? Doesn't mean you'll immediately see wrinkles. You don't get Euler buckling with 0 onset. This is what you will see. This will be the length of the wrinkles if the bending modulus was 0. If you have infinitely flimsy material, as soon as you compress, you maybe start seeing things, okay? But you see what we're trying to do now? Okay. Next, in the spirit of what you should do in this near threshold business, should I write this down? I won't write this down. I'll write the scheme down. I won't write the answers down. Oh, I won't write the algebra down. I'll just write but this is what we did. We started finding when is compression, and then when does the compression have to become failure? Okay? And in that failed regime, we started asking what's the wavelength. So what will you do? You will take these values of stresses. I'm going to erase all this. I'm going to take these solutions for stress. Now I'm going to turn on bending. I'm going to say, okay, now what is the effect of bending? And I'll put those solutions of stress in this long thing. I won't do it, don't worry. Okay? And ask if you put some guess for what the out of plane thing it should be, what wavelength will you get? Okay? This is a more complicated version of what we just erased. Right? This is B times the Q4 we got. This is a more complicated version of the tension. Okay? Remember, we did T over L square for the tensile substrate. But this is just same thing with more fancy-looking symbols. Okay? But actually, before I talk about that, the small thing I wanted to point out is this, which you can already see, is that if we're trying to write a phase diagram for this, a sort of phase diagram kind of thing for this, do you remember we only had one parameter in one dimension, which is delta over delta C. That told us everything. If I tell you the value of delta over delta C and the material, you know the answers. Now you need two things. This tau tells you confinement, like delta divided by delta critical. Okay? But now we need to know, remember this is nothing about bending in it. This is just about how much you've confined the thing. Now we need to ask, okay, I've put confinement in this direction. Is it going to buckle or not? And there you'll have a very similar buckling parameter. Buckling governed by we've written this a few times now. It's just the same thing. R in squared tension in, let's say. Okay? You remember we've written B divided by W squared T in many places as the place where this thing buckles. I'm going to give this a name. And I think it's actually quite nicely named, but the symbol was poor. So the word for this is called bendability. Yeah? Something with small b is very bendable. Okay? So you need two parameters now. You need you need this to tell, you need that to turn on confinement. You need this to say whether you're buckling. Okay? So this is to be contrasted with one dimension, where everything came in the same parameter. Okay? Okay, so what's the standard program we follow? Let me remind you of the standard program we follow. It's precisely what we did in 1D, but solve planar stresses. Those are the answers that we already wrote. Do you need me to switch color? White on white is okay? Yeah? So now go to take the normal Pople-von-Karman equation, the one with B4 derivative psi plus sigma times two derivatives things. Plug in planar sigma RR, sigma theta theta solutions. Okay. Put the solutions you got in. Just like we did in 1D. Remember, we found the stress in 1D, just Hooke's law, and put it in. Then assume wrinkles. Assume now that you have out of plane things, and you break, what's it called? That's right. He said rotational something. You do something like this. So this is the equivalent of the sine qy that we wrote down. And like we wrote down a small amplitude, this is a small amplitude, f small. Okay, so this is, you do this by perturbation. And now you can solve or scaling to get the best value of m. Okay? And I'll just tell you the answers. You can see what's, well, you can't guess the answers very easily, I don't think. But the answers are, what do I have? I have, well, we already got one answer, which is that the near threshold length divided by Ri, we got an answer for bending modulus equal to 0, okay, which is just that, the thing over there. It's going to have some correction. It's going to have some correction, and that correction is going to go like our usual bending over W, whatever it is. This is the same old 1/4 you've seen before. And you'll get the wave number again, just like we did Q. And this is going to look a little bit more complicated, unlike your, anyway, it doesn't matter. You're never going to remember these numbers. But this is the program that we followed in the 1D case, right? So it's not particularly interesting to me that it's 3/8 rather than something else. But we're following the same spirit of calculation. Right? Please. Yes. This means if you are this piece of material, that means your neighbors are pushing in on you. If you are this piece of material, your neighbors are doing this. Sigma theta theta is positive. This is under stretch. These things are under compression. And everywhere, because of the boundary conditions, everywhere you're under tension in this direction. There's too much material inside this dashed line. Okay, so you solve for where that dashed line is, assuming everything is planar. And then you say, well, now let me allow the thing to do what it likes, make wrinkles. And now I find out which is the best possible wrinkles state I can have. It's the same thing as we did earlier. Find out what the state of stress is when you're about to buckle. And then beyond buckling, you say what's the best wavelength I can choose. Okay? It just looks uglier. As I said, the answers that this thing produces for all the cases I showed and just erased, no, those things on the corner, turn out not to be good. And this was a bit of a puzzle. And the puzzle, I think, led to some realizations that are a bit broader than just the wrinkling itself. And I wanted to tell you what the resolution of the puzzle is. To think to the resolution of the puzzle, I want you to think back again to the 1D case we did. So what else did we do in the 1D case before we started doing things nicely? Before we did stretching, what did we do in the 1D case? Before we started doing the whole writing these equations, the simplest thing we did in the 1D case. I've got time. The clever kids in the front row say Euler buckling. So the first thing you do is the Euler elastica, right? We imagined that there was no planar stress that this thing could sustain. It just held its length, okay? And we did it just a pure geometry problem, okay? And then we did the whole painful thing and we found the geometry problem had done it correctly at very, very large values of compression. But it failed to get everything right about the transition. It got the transition point right. And you know, this expansion, the expansion above threshold, as I told you then, by good fortune, also got well beyond threshold correctly. I'll draw you the curve that I'm talking about, and maybe you'll remember what I'm talking about, since it's in the distant past now. We did this, and then we've started by doing this. Remember? We got a square root delta W curve, and then we said, okay, this is a bit fake. We have not allowed it, you know, we're allowing it option A or option B. We have to start from scratch. And we did this whole thing. And this is the right thing to do. Okay? You come here just like we did. You solve the planar state. You assume small amplitude. And you work out the solution, and if you recall, the solution is something like this. Okay? And you say, hey, miraculously, this is supposed to work up here. This was just square root delta W. It didn't know about the threshold. But miraculously, this works also quite far above the threshold. It needn't have, this thing could have failed. Okay, this is expansion around here. Okay, what I'm telling you is the expansion. This correct way of getting it seems to miss all the answers for this program of doing things. Yeah. Maybe I was going to do the calculation first, but maybe I should just show you data and show you how wrong it is. I'll show you one example. Excuse me for switching back and forth. We have data in all these cases. The wrongness of this approach and the correctness of the approach I'm about to show you is best shown in this case. So that's what I'm showing you data for. So here is the thing we talked about. You take, somebody stole my balloon. I had a balloon. Tell you. Okay, so the idea is you take an elastic thing and you put it on a spherical foundation, and now the compression is on the outside, right? Those red lines of latitude, they're too confined. And you start seeing wrinkling on the outsides. So you can do the similar calculation for this geometry. I didn't want to show you that because it's curved before you even start developing wrinkles. So you have to use the fuller version of these equations from the beginning. Thankfully, we have clever theoretical colleagues who did that. But this is how the experiment looks. You take one of these things, you float it on the top of a tube of water, and it's flat in the beginning. Then you control with pressure, you bulge this thing a little bit, and now it's suddenly floating on part of a sphere. Okay, and it doesn't like it, and it makes wrinkles on the outside. You count the wrinkles, you measure the length of the wrinkles, okay, as they invade from the inside, and you plot the length of these wrinkles as a function of the confinement parameter for this problem, which is going to look a little bit different than T in over T out. So this is that's a top view, that's a side view, okay? If you make a bubble, if you make it sit on a big sphere, it's flat and smooth. You curve the sphere a little bit more, you start seeing wrinkles. You curve the sphere even more, the wrinkles start invading further and further, okay? Yeah? So the length is a function of that confinement parameter. Say again? Inner and outer radius of the wrinkles. Yes, absolutely. So, as you change the curvature of the sphere it's sitting on, the length of the wrinkle slowly increases. Oh, they start at the edge of the film, sorry. This black thing is not the edge of the film, I'm sorry. The film is here. The edge of the film starts deforming. You start getting things from here. Okay? So these are for different thicknesses of film. The length of the wrinkles as a function of confinement. And this is the calculation we just did. We did it for a different problem, but that's the spirit of the calculation. It gets the threshold perfectly right. Here, no wrinkles. It tells you correctly when wrinkles will show up, but it doesn't get the length of the wrinkles right at all. Okay? And that came from this kind of calculation. This is the calculation we did on the board just now in a different geometry, but same type of calculation. You have radial stress and azimuthal stress. When the confinement is small, they're both positive. When the confinement is big, the radial stress as a function of radius still is always in tension. The azimuthal stress becomes negative at some point. So you say, okay, this is where it's in this region that wrinkles will form. So that's the calculation we just did. Okay? And that gets the answers. I think you'll agree with me, almost entirely wrong. Yeah? So I'm going to maybe tell you what you do to get the right, or what these folks did to get good agreement with our experiments. And I thought it was a very nice idea. So the idea is, let's try, you can do more complicated things, right? You can say, okay, I'm going to put one more term in F, could higher order. But what they did was, let's do something with analogous to the Elastica. Let's start with no bending energy at all. And let's see what you get when you are way up on this curve. All right? And let's see what kind of answers you get. We have many examples. What I showed you is polystyrene. Yes. Yes. This has everything to do with those wrinkles. They're the same origin. So you take your sheet of your paper, put it on top of a football, and try and bring it down. The qualitative origin is the same. You can do this experiment in a few different ways. You can do roughly what you are saying, which is take a sphere, take a plane, take another spherical shell and try to come down and stamp on it. Or you can do what we did, which is attach it to something that's deformable, which is the water drop, and change the radius of curvature of that. These are in detail different. In spirit, they're quite same. Okay. Okay. So I won't belabor this too much, but what you now do is, or what these folks now did, was the following. Now that I've got the screen up, I'll leave it up for another minute, which will also reduce the amount of stuff that I'll be tempted to write here. What they did was this. Here's the Lamé problem. They said, let's say the wrinkles have some length, okay? And let's say inside the wrinkle state, inside the wrinkle zone, there is like an elastica. You can just take care of any displacement without stresses. Okay? That's what happened in the elastica. So let's imagine the right way to start with this is not think of the planar state, but think about a state that can wrinkle as much as it wants to take away all the extra material. Okay? And then you say in here, sigma theta theta equal to 0. Okay? It's done whatever it needs to do to take care of all the extra stresses. Everything that is being pushed on by its neighbors has decided to leave the plane and be happy. Okay? And in here you solve for sigma RR, sigma theta theta in planar state. Right? There's no wrinkles here. Yeah? And what you must do is find this place by minimizing the energy. Just just move this boundary around till you have a minimum to this planar problem. Shall I be a bit more explicit about that? I'm going to start erasing. Was this the boundary? Was this the boundary or was this the boundary? That's the boundary? Okay, then I'll write in here. So what you say is the energy of radial stretching inside the wrinkle zone plus radial and azimuthal stretch outside L. Okay? Still no wrinkles. At least no wrinkles explicitly. No wrinkles at cost energy. There are actually wrinkles hidden over here. When I say there's no azimuthal stress, that's the wrinkles taking care of it. But there's no wrinkles in the algebra. You've set bending equal to 0. And then you minimize this and you find, let's call it L far from threshold. Okay? Once you've done that, once you've found the zone, then you go back and you do exactly the same thing. You put back wrinkles, but now not with the planar solution from the stable state, but with this new thing. Okay? And solve the problem again, get the value of M. Okay, those are all much smaller energies. All the bending energies are much smaller now. Okay? If you do things this way, then all of a sudden you have much better agreement with the experiment, which is a nice thing always, no? And in general, the same approach solves all those problems. Okay? So what's happened here is, you get the idea. This is the problem you solved. In the first instance, this is the problem you solved. You said, I'm going to take the stable state and I'm going to find where it's compressive. Okay? In the second instance, you solve this problem. You say by hand, you say the stress is 0 inside where the wrinkles are and solve the rest of the problem. Okay? And this gives correct answers. Now, many comments I have to make here, which are probably more useful than any algebra I've shown you. Let me talk for a few minutes about this new parameter that's popped up, which seems to make a difference. You should understand that these experiments are by no means the first experiments to produce wrinkles in radial geometries. So it's not that it's not that near threshold calculations have never worked. I mean, engineers have validated them for ages. I mean, there's a reason that they've been used. But now I want to point out to you why things seem to fail so badly. And to do that, let me talk a little bit about this parameter. So we saw this one earlier in the 1D wrinkling problem also. But in the 1D, this and the confinement ended up being exactly the same thing, okay, if you recall. But let me first point out a couple of things about this. I think it's a nice phrase, but it's unfortunate that its inverse was the thing that got defined. So we're always talking about inverse of something. So the bendability is this times some force divided, some size times some force divided by. So first thing is, unlike the von Karman number, which is just size over thickness squared, this thing has some information about external forces. Contains I think this goes back to the question that somebody asked here, how thin are these sheets? What's the dimension? I told you the von Karman number is 10 to the 12. Okay? This is the place which is huge, right? That means really thin. This is the place where these calculations should work the best. So it's not any failure of the thin approximation. It's much better than airfoil of an aircraft or a wall in a building on grounds of thinness. Okay, but it carries different information. So I want to write this in a few slightly different way. If you recall, this is Young's modulus times thickness cubed. I'm going to write this as Young's times thickness cubed, attention. And now I'm going to write this as, I'm going to keep one of the t squares, and I'm going to make the other t divided by y. This is E times t. This is the stretching modulus. Okay? Is that what you're commenting on? That's incorrect. Thank you. Yeah? Okay? So this is this is von Karman's number. This guy is, what is this going to tell me? This is how much I'm pulling, and thank you. It's like the strain. Everyone's okay with this? This number is big for thin objects. It's the very definition of thin almost. This is small, typically in elasticity. Right? So you can be a thin plate and you can have very large bendability or not very large bendability. This number can be anything, is the point. And I think it immediately says that, it forces a realization that wasn't around so much, that there are limits to this equation to think about. There's a large bendability limit and a small bendability limit. The thin plate equations are perfectly valid for both, but they have a completely different behavior. I forgot who asked. So strains typically in these experiments are really small. Okay, I mean, usually the elastic limit for materials like polystyrene, for example, are 0.1% strain, so 10 to the minus 3 or something like that. For material like this, you can get more strain out. But it really depends on how big this thing is. You can be perfectly well in elasticity, you can be perfectly well in thin regime, and this number can be much bigger than 1 or much less than 1. Okay? For the materials I've been showing you, this number is much bigger than 1. That means it's very, very bendable. You can do good, solid engineering mechanics with sheets that follow plate equations perfectly, but where this number is quite small. Okay? So really a way to think of this is that that's in a terrible corner, no? But let me just, okay, let me not. So let me just write, the shorter kind of form of these equations that we've been looking at, with some forces di dj sigma equal to normal forces. Okay, this thing is roughly, I don't know. You get you should get some. You're balancing this term, and this, this is sort of the scale of this. The scale of this is some tension time and you can see this is where epsilon comes from. It comes from 2 different terms in the equation. And what the lesson is, you should please make up your mind what is important in the problem. It's going to be exceptionally unlikely that these are equally important in balancing external forces. Probably one thing is going to be important or not. So when you start off, you're looking at whatever you're looking at, please calculate this number. And then it tells you something about the underlying physics of what's going on. Is it stresses, in-plane stresses that are balancing the outside thing, or is it the fact that you can't bend this thing that's balancing out-of-plane forces? So it really it tells problems apart. A lot of the intuition, I don't know, I started off, the first time I ever learned elasticity was not in a physics class, but the first time I learned was in a civil engineering structures class. And I'd long forgotten. I had to relearn it when I started working in this stuff. But there the intuition had always given is you're working against moments, and the moments are provided by the stiffness of the material. That's not what's going on here. It's some internal stresses that you're always fighting against. So the geometry takes the internal stresses and gives you something to work against. So I think that's the main set of things I wanted to tell you about with this. I mean, if it's a helpful analogy, I don't know if I have that slide somewhere here. Yeah. I don't know if it's a helpful analogy, but my colleague always shows this slide. And it's borrowed from him. You should maybe think of it like this, right? You have some equations of fluid mechanics, they're the Navier-Stokes equations, and in their generality, they're huge, scary equations. But there are limits to them, right? And there is limits in which you have very low Reynolds number, and then limits in which you have inertia. You should think of things in the same way. You should think of things in the same spirit, if you have things that are very bendable, those things cannot support any compression. There's no point starting from a planar state that can support compression and working with them. Whereas there are things that are not bendable, in which this is the right, the standard way of thinking about things is the right way to think about it. And now there's a parameter that tells you where you are in this way of thinking. So more than any of the specific configurations of wrinkles that I've shown you, I think this is a useful thing to know. It's a useful recent development to know about. It gives something kind of amusing. Oh, sorry, I didn't want to do that. So I haven't shown you much of what happens in this problem, but it does give you something amusing. So when you normally think of pattern formation problems, this picture that I erased is actually a good way to think about. This is some order parameter for the pattern. This is some forcing for the pattern. You should figure out what's happening when there's no pattern. You should expand in about here. And then if you have energy, you should expand more and go more and more. But here, there's a regime in which you can do that. You see, you go from the smooth boring state into a wrinkle shape in which there is a near threshold regime, and then maybe something else happens. By the way, there's a completely fictitious set of blues and pinks here, but just to give you an idea. But there are situations at high bendability where as soon as you go into the pattern state, you've forgotten everything about the planar state. So there's no point in making expansions around this. And the regime in which the validity of near threshold kind of calculation just goes away completely. So it's this kind of unusual thing to see in pattern formation, where there's nearly no regime of where you can see interesting things. I haven't told you about the yellow at all, but that's a separate issue. So we talked about 1D wrinkling. Then we talked about how a delocalized solution in 1D becomes a localized solution in 1D, right? We talked about folds. I'd like to now begin doing the same thing for 2 dimensions. We talked about how now a general state of stress in 2 dimensions can make wrinkle patterns in 2D. I want to now talk about localized objects that you cannot see in 1D. Okay? So 1D we saw folds. 2D you start seeing other kinds of sharp solutions, right? And just give you some flavor for what their energetics is. Yeah. These are completely irreversible. I'm not going to talk about the irreversible. This is a good point. The thing you do this most with is paper. And as soon as you do it with paper, you realize that this is plasticity. And it's a good question to ask. I'm going to now ask, for example, what is the size of this thing? Okay. Once it's plastic, the characteristic size of this thing is the thickness of the piece of paper. If I ask, if I do that, and ask you, what's the width of that thing? It's going to be set by something microscopic. It's going to be set by probably something on the order of the thickness of the paper. Let's do it with this. I think you'll agree that you get similar structures. So the argument is probably that in the cases where it's plastic, like tin foil or paper, that there was an elastic object before that set the geometry of this. So you're squashing some elastic object, it was going in a certain way. At some point, the strain became too much, and it said, I'm freezing in the strain. So thinking about the elastic version of this is useful in going up to the point of plasticity. The energy of that plastic object is obviously different. Any elastic calculation is not going to do it. But I guess it's also worth thinking about the elastic object itself, because there are many situations in which the object that is being crumpled is elastic. Right? Probably every situation that you want to think about a biological membrane undergoing this kind of compaction is reversible. The thing that you most often are shown is explicitly irreversible. But I think they would argue that, hey, please pay attention to the elastic argument anyway, because it's going to tell you something about what happened before it became irreversible. So the first thing I'd ask you to do is, let me take a piece of paper. Let's look at this a little bit carefully. Let's make one of these, okay? Okay, and you can all try it. If you try it, you'll find that this thing is not flat. Okay? This thing has a curve to it. You don't have to believe me. You just have to ruin your notebooks. There's a curve to this. Okay? There's also a characteristic curvature in the opposite direction. You can impose whatever angle you like far away. It's not going to meet at that angle close by. It's going to soften. There's going to be some radius of curvature that will develop over there. I should say some general point. These equations have been known literally 120 years. I think Fabel von Karman was written in the 1905 or something, or 1907 or something like that. All these solutions are very recent, and it's just I think a sign that to extract physics out of nasty-looking equations needs actually a lot of just thinking about it. The ridge solution was, I think, the first solution for the ridge was published maybe in 2001. And as we'll next move to the other object, which is the cone, which there's still some things that are not quite figured out. The 1D thing, the general 1D thing that we wrote yesterday is early 2000s. It's not that these weren't mathematicians. It just took a lot of simplification and finding what the right thing to calculate was, Sorry. So now let me talk about the ridge. So I want to say that the ridge looks something like that. And I want to follow an argument from... It does, doesn't it? Maybe 2001? I put the Whitten. This is a different Whitten, not the Whitten who gets talked about in this building more often. But, and I think also a very... physicist with serious contributions. Yes, it is saddle-like. Take a look, take a look, take a look, take a look. Look at your shirt. Saddles all over. So these do have a solution. Simple is a matter of your... they're not simple for me. There is now a similarity solution for these things from about 2 or 3 years after this. So what I'm claiming is if the size of this ridge is what we've been using W, right, for how big things are, is W. Then it always will sag by some amount, and it'll develop a radius of curvature here. And what we'd like to do is some estimate of how much that sag is and how much that radius of curvature is. The only real things you're controlling in this, when you make the ridge, is how big the ridge is, right? You might control W, and you might choose to control the angle and the side if you like. That's right. You don't control how sharp that is, right? It's not externally controlled. It develops some radius over here. And it develops some sag. You can at most control maybe what the faraway angle is, and you can control the distance between the fingers. Okay? So, okay, good. So, looking at this from the side, at a cross section here, this thing will look. This is some alpha, which you can control. And this is that radius of curvature that I was trying to draw. So it's probably not a good thing to have drawn it here. This is where you actually pinch it, no? I want to draw the radius of curvature here. The other side of the saddle. Yeah? So in this picture, alpha and X are, alpha and W are imposed. And R and delta develop themselves. Yeah? So first thing to realize is, if this thing sags, there's a strain along the ridge. Okay? You don't, okay. Do this and see if you see daylight. Yeah? It's small, but it's, there's actual strain over there. You need 2 cones to pin it, right? We'll talk about the cones next, because obviously that takes energy also to make the cones. Huh? How are we on time? We may or may not talk about the cones today, but let's talk about the ridges. So let's try and figure out roughly what the strain is. I'm going to do my usual approximations to curves. I'm going to make them into 2 right triangles. Okay? So the strain is okay. That's what the strain is along the ridge. The strain along this line is about that much. The next piece of information I want to extract is a little bit about this R. So this thing is R. I'm going to look at that little triangle and I'm going to say that, that's a horrible picture, sorry, but something like this goes as sine of alpha. Okay, I'm just looking at that triangle up there. or delta over R is some function of alpha, some tame function of alpha, sine alpha minus 1 or something like that. Okay. So now not energy densities, energies, right? This is one localized object. The energy of stretching is half y times strain squared times the area over which the strain is spread, half what was it? Oh, yeah, I got that, yeah. Squared times, I don't really know what to do, but let's say that this whole area is relevant. We're at a high level of hand waving here again. No? It agrees with the similarity solution though. That's the area over which the strain is spread, roughly speaking. Again with a, again roughly speaking over the same area. So this is did I do that right? I think so. So this is some proportional. I'm going to now replace the deltas by r's and some function of alpha to some power, okay? So this is r4, r 5 powers of r, and w cube, and this is b times w over r. Okay. Minimize bend plus stretch. And so I'm minimizing with respect to, what does the material get to minimize with respect to? What does it get to choose by itself? It gets to choose the radius, right? So I'm minimizing with respect to r. And I end up getting r goes as width to the 2/3 with some coefficients. So the thing I wanted to point out is the following. Actually, I should probably keep b over y also here, because b over y is actually interesting here. It's b over y to the 1/6. Let me just check dimensions. B over y has dimensions of t squared, thickness squared, right? This is et cubed, this is et, t squared. Yes. So this is t to the 1/3, width to the 2/3. Okay? Is the radius of curvature. The thing that you want to see is, if you want to ask, is this really localized? Let's just say, does this object occupy a vanishingly small fraction of the area? Then the answer is yes. Of bend plus stretch is, this is the fraction of the area divided by total area. And that's, you know, this thing has a d to the 1/3 where did we go? I'm really sorry. Yeah. Did I get that right? No. So this goes as thickness over width to the 3rd. So as you make a sheet thinner and thinner and thinner, the ridges occupy 0 area fraction, is the idea. Okay, so these are truly localized objects. And I think this was originally, I think Witten originally started this calculation right after, fullerene molecules were discovered, and these things are they have 5-point defects, and they look pretty spherical. And the question was, suppose you make larger and larger and larger fullerene balls, what's their asymptotic shape? And then he went and found ridges between those points. So if you work with fairly small size objects, these things won't look sharp. As the separation in scale between the thickness and the width becomes larger for exactly the same material, you'll start seeing, things look very sharp and well defined. Okay, so the small thing remaining that I wanted to do, which I'll do tomorrow, is the other part of this, which is the folds. I also haven't discussed for you in 1D, we discussed what happened when you went from a localized to a delocalized situation, from a delocalized to a localized situation. I haven't talked about that transition at all here. I told you one thing, and I told you another thing. Okay, and I haven't told you how you get from one thing to another. Okay, but we'll stop there.